sometimes doesn't carry a lot of information either, right? Because what's the chance of us winning, right? So you have realistically, self-information is not enough. You have to weight the self-information, right? What is the actual chance that something like that can actually happen? Okay. So in this case, you have to take p times I of p. Okay. So this is the weighted information. Negative p times log base 2 of p. Okay. Now in this case, as you can see, the weighted self-information first increases, and then after a while it starts decreasing again. And it's going to be 0 at both ends, right? Because something that never happens in a weighted sense is useless, right? It carries a lot of information, but it never happens, right? So in that case, it's useless, right? So now the values of p turns out to maximize this, and you can easily take the derivative and show, right? That is something like this. It happens to be 1 over the natural number e, which turns out to be somewhere around 0.378 or something. Okay? And that gives you the maximum weighted self-information. So somewhere around there is the case where doing very good compression is very tough. Okay? Something actually happens, but it's hard to predict. Okay? When it's clear to near 1/2, it's very tough. So the next concept is this, is entropy. And entropy is nothing more than the summations of all the weighted self-information. Okay? So for this source, okay, for example, in the image case, you might have 256 values, 0 to 255. Okay? And the probability of something happens, okay, of some pixel having a certain value, like 218, okay, can be computed like this. P of x of I, the probability of it happening, multiplied by negative log base 2 of P of x of I, which is the self-information of that random variable. Okay. Another notation that we sometimes use is this, where little x belongs to the large X, which is the set of all the possible symbols that can happen. For example, in the alphabet case, A, B, C, D, E, F, G, H, okay? And then the probability of x means that the probability of x equal to one of the guys in large X, and times log base 2 negative size of probability of x equals to sum of the element in X. Okay, so this is the shorthand notation that we use. Okay, the unit of entropy is bits per symbol. How many bits do we need to encode one particular symbol? For example, x1. Okay, and this famous formula, this formula for communication first appears in this Klaus Shannon's classic papers, Mathematical Communications, in Bell System Technical Journals in 1948. This is the birthplace of information theory. Okay, and without Klaus Shannon, we will not have digital communication nowadays. Okay? Everything is based on this fundamental papers. Now let's take a look at an example of entropy. Okay, find and plot the entropy of the binary code, in which the probability of occurrence for the symbol 1 is little p, and the symbols for the symbol 0 is 1 minus p. Okay. So first of all, the summation of 2 probability gives you 1. We only have 2 symbols. Okay. Either 1 or 0. You cannot have negative 1 or 2 or 3. Okay. So this is a binary source, which we will encounter a lot of time in practice, right? So now I only have 2 symbols, right? So the summation only goes from 1 to 2, and the probability is this, right? P of x of I log base 2 of P of x of I, and if I substitute P for 1 in and 1 minus P for 0 in, I have this function, okay? And then plot this, okay? How do we do this? We can do this easily in MATLAB, okay? Or we can still do it by hand, but it's a little tedious, right? So let's take a look at a few interesting cases, okay? If P turns out to be 1/2, P is 1/2, then you substitute 1/2 in here, okay? You have negative log base 2 1/2, which will give you what? 1/2, right? Will give you 1/2, and then the other guy will give you another 1/2. So 2 1/2 add together give you 1 bit per symbol. So what Shannon say is that if the probability, if you have a binary communication, you have a binary source, okay, where the probability is 1/2 for 1 and 1/2 for 0, basically there's nothing you can do. Okay, the entropy is 1 bit per symbol, which is the lower bound of the compressions that we get. Okay, so this is the amount of information being carried in that source. Now, if you have P equal to 0, then you plug everything in and you get 0 bit per symbol. Okay, this is the trivial case where we throw the coin that's not fair. Okay, we come up with tail all the time. In that case, there's no information. Okay. Well, you can argue, you can hand wave that 0. Okay, log base 2 takes a longer time to get to 0, so it will be dominated by the 0. Okay. No, you can take limits when P goes to 0, okay, and show that this limit is actually 0. Right?
How to calculate in MATLAB?
No. Yeah, it will be tough to. MATLAB will complain. Okay, although it will give you 0, it will complain that you are taking more. Okay. Now, if P is equal to 1/4, okay, then you plug everything in and you get this, which is a pretty interesting number. 1/4 means that you are being dominated by 0. Okay, you have more 0 than 1, and there will exist a magical code out there that's somehow being able to deliver 0.8113 bits per symbols on average. That means you can do better than just assign 1 0. Okay, there is something out there. Now he never tells us what do we do to get this 0.8. Okay, that's our job. Okay, but the lower bound for that source is this. Okay, now if I plot it, it looks something like this. Okay, so the maximum you achieve is at 1/2, minimum you achieve is 0 and 1, perfectly predictable. Okay, now. So before I move on, does any of you observe anything wrong with this? Can you come up with a counter example with probability being 1/2 or 1/2 or 0, but carries no information? Is there such a thing? Is this true all the time? What kind of assumption that he's making? What about this example? What if I have a source that looks so for DNA sequence we have 4 symbols A, C, T, G. Okay, and if they are equally likely to happen, okay, if the number of A's and number of C, number of T, number of G's are exactly the same, they have no inter-symbol correlation. Okay. Then the entropy of this source turns out to be 2 bits per symbol, which is very intuitive, right? If you want to send this sequence over a communication channel using binary codes, maybe the only thing we can do is A being 0, 0, C being 0, 1, T being 1, 0, and T being 1, 1. And that's it. No compression is possible. But if we have something like this, where A, half of the time you have A, 25% of the time you have C, and 12.5% of the time you have T or G, then the entropy